this presentation on ultra-thin, unsinkable, Janus-phased solar thermal interfacial evaporator for high-throughput seawater distillation and solar water production. Earth contains approximately 1.4 billion cubic kilometers of water, yet less than 1 is fresh and accessible. Conventional purification technologies are energy-intensive and unsuitable for many rural settings. In contrast, solar stills utilize freely available sunlight for purification but remain inefficient in terms of output. We designed a unique interfacial evaporator called NCFPH, which integrates nanostructured hard carbon fluorides with a porous polyhype scaffold. Polyhype membrane features a three-dimensionally interconnected network of pores that continuously transports water to the surface. To this unsinkable scaffold, we spray-coated nanocarbon fluorides that act as a broadband absorber, capturing nearly 96% of sunlight and efficiently converting it into heat. Under solar irradiation, the NCFPH surface rapidly reaches about 120 degrees Celsius within 200 seconds, enabling instantaneous water evaporation. Engineered Janus-phased NCFPH with hydrophobic and hydrophilic properties for salt rejection and water transport. Subsequently, we complete the water cycle by condensing the vapors on a hydrophobic Peltier device surface and collecting fresh water with higher output and power efficiency. NCFP demonstrated a rapid water evaporation rate of 5 to 6.5 kg/m² when using different saline solutions. NCFPH material achieved a solar thermal energy conversion efficiency of 84, meaning it effectively converted sunlight into heat and delivered it to the water molecules. Moreover, this evaporator also effectively rejected salt, with over 90% of the salt remaining behind after the evaporation process. Electronic microscopy and X-ray imaging analysis of NCFPH further confirmed that salt deposition was minimal within the water transport channels, ensuring consistent water flow and does not impede the water evaporation ability over time. In the SunSpring prototype, we generated freshwater that meets EPA standards from highly saline seawater for over 225 hours of continuous use at a rate of 18 liters square day. The NCFPH material is an ultra-thin membrane with 80 porosity, allowing it to float on the water surface. Janus-type design effectively absorbs sunlight and generates heat, while the other side facilitates continuous water transport. Computer simulations suggest that the low thermal conductivities of NCF and pH facilitate the concentration of heat at the water-air interface, thereby facilitating the transfer of heat to the water droplets and promoting continuous evaporation. We investigated the local structure of water at the interface using Raman spectroscopy, which revealed that NCFPH primarily fosters the formation of intermediate water. Such loosely held water clusters evaporate rapidly as their latent heat of evaporation is significantly lower than that of water. Developed system-level prototype called SunSpring primarily separates the evaporation and condensation processes. The NCFPH interfacial evaporator and SunSpring represent a significant advancement in sustainable freshwater production. The device combines high solar thermal energy conversion efficiency, rapid evaporation rates, and efficient salt rejection with excellent freshwater production. SunSpring prototype demonstrates the potential of this technology to deliver clean and affordable water to areas experiencing water scarcity.